complete design of a 5-story concrete building series of 3 webinars. We're on the third and final part, in which we will focus on the design and analysis of the required reinforcement. You have the opportunity to communicate with us via our contact email shown here in the upper right hand corner as contact@casolutionscompany.com. The content of this webinar has 3 main portions: the superstructure building design, the substructure building design, and a bonus forensic study of a failed concrete using nonlinear advanced analysis. The superstructure consists of the concrete beams, concrete columns, concrete slabs, concrete walls. The substructure building will be the circular isolated footings. Now, the building has been designed in its entirety in the previous 2 webinars, and we can have loads from such webinars to be applied in the design analysis of a reinforcement steel. For the unfamiliar of the audience with CivilFEM 2016, it is a CAE productivity tool that works for you. All you need is included in one software package. CivilFEM 2016, powered by Marc, is a complete CAE FEA product with its own solver, Marc, that combines the ease of use of a modern GUI, graphical user interface, environment with multilingual analysis tools for professional and academic users worldwide. Using the MSC's Marc powerful calculation engine solver, CivilFEM 2016 is able to perform complex analysis such as high nonlinearities together with structure analysis and or evolutionary construction processes with great speed and accuracy. Our company, CA Solutions, is the representative of this powerful easy-to-use software package. What is CivilFEM 2016? Imagine a company at the center of this view graph. You have around the perimeter different departments. Starting at 1 o'clock, we have the steel and concrete structures and seismic analysis department, following by the nuclear power plant department, foundations and tunnels, and graphical department. Then you have the bridges department or infrastructure and the hydraulic works department. What is CivilFEM 2016? The applications. You can use it for the solution of seismic design, checking and validation, energy, power plants such as nuclear, wind turbine, and thermal. You could do harbor, offshore, and naval structures, nonlinear construction process, structure analysis, tunnels, out of the infrastructure, foundations, such as retaining walls, piles, surface foundations, rock and soil mechanic analysis, hydraulic dams, concrete and loose material. This will be part of energy power plants, structures and bridges, which will be reinforced concrete, steel, pre-stressed and post-stressed, reinforced concrete, tender stay, etc. Again, structures and bridges is part of the current interest in construction, which is infrastructure. Cable structures, non-residential buildings, industry plants, skyscrapers, sports stadiums, quality control and procedures in construction works, forensic structural analysis, which is a way to determine how structures failed, and project redesign, check-in and validation. The model that we are going to analyze and design the reinforcement steel is presented here in the plan view. You have the circular portion of a building with the circular segments in light blue representing the walls. Then the apple green represents rectangular columns. Notice that the circular building has circular columns. So we have two buildings, the office building on the left in circular form, and we have on the right a rectangular building joined by elevated slabs. Now we'll proceed to the last part of the study to demonstrate how CivilFEM is able to analyze given steel reinforcement, and then if not sufficient, it'll design by selecting the amount of steel required to for those who have not seen the first two parts, this is a model as it appears. The colors green and gray are intended for visualization, but they represent the circular slab of the circular building. The red color represents the walls, and the blue color represents the slabs of the rectangular building. Slabs are represented by plate elements or shell elements. Observe the continuity of mesh at the boundaries between, say, the green and the blue, the red and the green, and the gray and the green, and the corresponding connection to the beams and columns, to the beams, and the columns for the walls. The first thing we're going to demonstrate is that while we demonstrate that it has several codes, we will select a particular one for this webinar demonstration. These codes are concrete type and steel type material. These are the codes for concrete. In this instance, we're going to use the ACI 318 for American Concrete Institute. For the steel material, we have all the primary codes. The model has all the material properties defined. We show the concrete material properties, which on the left shows the details. And these are the properties of the code utilized for this design and analysis. We have also defined the steel properties for the reinforcing bars. Similarly, we'll see the properties at 60 KSI, yield strength, this model also has loads that have been assigned in the previous two webinars, which consist of light load, gravity loads, which is self-weight, okay. And we have introduced in this webinar a spectral analysis on the left-hand side of the properties for the spectral analysis. We are requesting 12 modes of vibration. And here we can see the graphical display of the spectra. CivilFEM will calculate the 12 natural frequencies, the corresponding mode shapes, and combine them based on user preference specified by the user. In this case, we're using SRSS, square root of sum of squares, summation method. We could display the load graphically. And we can see also the supporting of the structure. And the loads on the plates, elevated slabs. For the cyclic analysis or seismic, the masses are calculated automatically. We have also defined sections for each structural element. We have the circular section corresponding to the circular columns at the circular building. We can visualize that we have placed a number of rebars around the perimeter of the column. This steel will be used to check the capacity of the columns, and later on we can figure, with the assistance of CivilFEM 2016, whether we have placed sufficient reinforcement or whether we are in excess or deficiency of reinforcement based on the codes check. We have two options, either to check the existing provided rebar reinforcement or have the program design it for us by giving us the square inches of steel reinforcement per foot of concrete membranes. We can define axial as well as shearing steel in one model. The second section that we have defined are the rectangular columns in the rectangular building. And last but not least, we represent here the silver reinforcement selected for the beams. This is a brief review summary of what was performed in webinars 1 and 2. Now we'll see the results for the analysis that will be representing today. The analysis was already executed and the results have been saved to save time in this presentation. All I have to do is retrieve any particular results file. In this case, we're going to see the displacements due to the spectral analysis, which means the lateral and vertical displacements. Again, this will be seismic analysis results. We will see that the displacement is maximum in the lateral direction. The upper right-hand corner shows a maximum displacement in inches of about 4.5 inches, which shows 4.4. Now, we will look at the motion vibration. As we stated previously, we have requested that CivilFEM computes the lowest 12 modes. Keep in mind that the ASE 7 has a criterion for which a building is defined as either rigid or flexible, which is a frequency of 1 Hertz. This is the second mode of vibration. We can change the modes dynamically. Now we're going to affect the design. Similarly, you have other results that can be viewed later, such as moment diagram, shear, torsion, the reactions of the foundation, the loads in the elevator slabs, etc. The design would require that we perform an envelope of loads of the run cases that we already have saved. Your combinations were defined based on building codes such as ASE 7. We're going to retrieve the pertinent files. Once the design load combination have been created and saved, one can create an envelope such that the program can extract the maximum and minimum moments and forces based on combinations envelope. On the left side, we have all the load combinations that will be utilized to create an envelope of loads. Now we can have the envelope opened and read, and we can see the results. In this case, maximum values based on the given load combination for the design of the reinforcement by CivilFEM 2016. Now we will proceed in the design of the reinforcement. The check mark represents a request for CivilFEM to tell us whether we have placed sufficient steel, too excessive, or deficient. The question mark would say to CivilFEM, please provide us with the required reinforcement satisfying the pertinent building codes. Before we proceed to this portion of the webinar, we'd like to explain from PowerPoint pertinent parameters. The axial and bending check design is the paramount parameter required to provide us with whether we have adequate steel reinforcement. The strength design criterion is defined as a ratio between the distances within the interaction diagram, as shown in the distance from the center of the diagram, called point A, or the figure on the left, to the point representing the acting applied forces and moments, point P of the figure, which is labeled as D1. And distance from the center to the point representing the ultimate allowed forces and moments in the criterion definition, point B. This distance is defined as D2. The criterion, the word criterion will appear in CivilFEM, is the ratio of D1 to D2. If the criterion is less than 1, that is a fraction between 0 and 1, the forces and moments acting on the column will be less than its ultimate strength limit, and the column, therefore, will be safe. Otherwise, the column is obviously considered unsafe. Easily, CivilFEM will liberate us from any hand calculations. After a loading of the RCF results file, the user can perform a code check or design using the results from the loaded results file. Again, the loaded results in that case is the envelope of the load combination specified. By clicking on the corresponding icon, the user will be able to select the design options. These icons shown in the middle of the view, the check mark represents checking the provided reinforcement. This is called analysis. Could be applied a question mark saying, give me the necessary reinforcement. This could be for columns, beams, and plates. The check mark represents check beams, or we can have the program CivilFEM provide us with the reinforcement in square inches per foot of concrete matrix. Now we'll proceed to perform the design of the reinforcement. As we mentioned previously, the most critical values from the envelope results will be utilized to analyze and design the required steel reinforcement. Note that to check the defined reinforcement, CivilFEM can perform the bending, torsional, and the cracking of the concrete. In this case, we'll check the bending and shear. We press OK. The program initiates the check. CivilFEM just completed the check, and we are proceeding to view the outcome. The results are generated on the basis of the criteria that we defined or explained previously. For better visualization, we're going to remove all the plate elements, which are the walls and slabs. And display the results deformed. This will give us a feel for the reinforcement, as we will see that where there is maximum deflection, there will be some maximum reinforcement. In this case, we're going to hide the walls and slabs. For a better visualization of the reinforcement of the columns and beams. Here we can see the 12 criterion, and obviously, as we stated, the criterion should never exceed 1, and as you can see, the column at the base is exceeding 6. We can easily have CivilFEM determine the required reinforcement. However, we will proceed to show the design and analysis of reinforcement for the slabs. The 12 criterion was defined before, and as you can see, the red represents excess of 1. And it shows the results of CivilFEM as it evaluates our design, meaning that we have specified some initial reinforcement square inches per foot of concrete matrix. It is also possible to perform the design, I'm going to ask CivilFEM to calculate the required civil reinforcement based on the applicable code chosen. Now we're going to activate all the elements, and we want to visualize only the walls and elevated slabs, which are shell elements or plate elements. Now we'll proceed to design the reinforcement required for the plates representing the elevated slabs. For outer plane, we would have reinforcement at the top and the bottom if we had all the loads, but we're going to do only dead load, and therefore the reinforcement is going to be at the bottom of the slabs. Again, as we refer back to the Criterion definition, we see here that the load would be reinforcement in the X direction for outer plane loading, reinforcement in the Y direction perpendicular to X for outer plane loading, and for the shearing strength of the plates, we have the mid-plane loading of the shell representing the elevated slabs. There are different methods of this designing the reinforcement for the slabs. Just as we stated in the beams and columns reinforcement design analysis, same options are available for the shells representing the elevated slabs and also the walls. Here are the different methods that are applicable to calculate the reinforcement for capacity and to avoid cracking or minimizing. This information is clarified in the user's manual, where each method is explained with applicable equations. The advantage of CivilFEM is that you have all the required analytical tools in one software, from analysis and design, applicable to the areas of forensic and also design for fabrication. Now we're going to perform the design for the steel requirement of the elevated slabs. CivilFEM would rapidly perform this design, as you can see. This was an actual calculation in real time. Now we see that CivilFEM will save the results in both directions, X and Y top, XY bottom. Again, there will be reinforcement top and bottom because the seismic analysis will perform a vertical loading, not just downward, but also up. The results are, CivilFEM is very flexible in units. Normally, the results are representing as square inches of steel per linear foot of concrete matrix. Now we can see the zone where the reinforcement is required. The colors represent the magnitude in units of square inches per foot. We can see very readily that most reinforcement is required about the points of support, which are the columns. Similarly, for the walls, you can see that it happens at the edges. Now we are seeing white bottom in square inches per foot of concrete. Again, the maximum color of red represents the maximum reinforcement. Notice also that the load interaction diagrams for the columns can be obtained automatically. If we wanted to know the interaction diagram for a particular element, such as a beam or a column, we simply select it. We can demonstrate the interaction diagram. For element and there it is. The red line represents the limit of the criterion, and the blue represents the actual load. As you can see, we have approximately 20% capacity left in the material. Notice that the column is working as a capacity of 50%, which represents a factor of safety of 2. At this point, we have completed the design analysis of reinforcement steel for the beams, columns, slabs, and walls. Now we'll demonstrate how to design an isolated footer. This design is very exciting because it includes the soil, and we can assume that we have about 2,000 pounds per square foot capacity, and we will show that we don't exceed this capacity of the soil. Here we have a three types of model. The amber represents the soil, and it's chosen to have a diameter about 10 or 3 times larger than the depth of the slab on ground. The small circle represents the isolated footer, and the center represents the column itself, a particular column. In this model, we have defined 3 material. And please note that we have selected this particular column because it has proven to be the maximum load of the sets. We have here the different kinds of material. We have the sand for the soil. The concrete is 5 KSI compressive strength, and the steel, as we stated before, 60 KSI yield strength. For the soil, we have assumed to be sand clay. However, CivilFEM has built in other materials as well. Notice that for the plastic behavior of the soil, we are dictating or stipulating that Drucker Frager model is used. Also, you have the predefined soils such as rock. For rock, we have sub-classifications as shown here: sedimentary soil, igneous, and metamorphic. We have CivilFEM has a great variety of soils already built in, which frees the analyst from having to perform, investing time in determining the properties for a particular project. In this building, we just performed the maximum envelope load at the center. Notice the boundary conditions. And again, even though the building has the capacity to show vertical displacement upward and downward for the soil, or we select the downward. We also have to find a contact between the isolated footer and the soil. CivilFEM has the ability to perform different types of contacts. Now we can see the results. First, 1C settlement. Of the isolated footer and inches. Notice how the isolated footer presses on the soil, and the color red represents the maximum vertical displacement of sediment, building sediment. Normally, you can have industrial piping between buildings, and this becomes a load for such a piping system, for instance. This vertical displacement is approximately 2.5 inches downward. We will also demonstrate the bearing load and compare such a load in pounds per square foot to the allowed soil, which is normally 2,000 psf. Among other results available, we can see the elasticity of the soil. We can see how the soil is displaced inelastically. Similarly, we can define how we previously performed it with the plates, that means elevated slabs and walls. For simplicity, we only perform the gravity load, which means that the reinforcement that we're going to obtain is for the bottom reinforcement. And because the plate is circular, X represents radial reinforcement as spokes in a wheel, and lateral X will be theta or angular. At this point, the X bottom represents square. We need to change this. Let me change this to square inch of steel per foot of matrix. Sorry about that. Now we have the display in square inches of steel per foot of matrix. Now the bonus portion that we have promised has to do with forensics failure that we are studying using CivilFEM. We perform this analysis using nonlinear analysis features of CivilFEM, and we'll demonstrate the cracking, which is the initiation of failure, and the ultimate crushing of the concrete in compression as the tension steel failed. This model represents an advanced design and analysis feature of CivilFEM 2016. The column and the beams are modeled with concrete solids as the matrix of the material, and the rebars are embedded into them using the feature insert of CivilFEM, which minimizes the effort required for compatibility of nodes at the interfaces of the rebars and the concrete. For this model, we have also utilized concrete gap elements called glue model. As we can see, keep in mind that the use of gap elements is nonlinear because when there's a detachment of one material to the other, the overall stiffness changes. Please note that the bars were inserted into the concrete matrix using the feature insert of CivilFEM. Also, we define the concrete the cracking and crushing. Cracking will be for tension and crushing for compression. We have applied loads and boundary conditions. Now proceed to see the results. The program would progress from 0 to maximum until it detects cracking and then continues to crushing, at which point it terminates. Now we're going to see the cracking strain. Here we can see the cracking region in this zone, similar as shown in the photograph provided to us. This shows that when the failure was initiated with the cracking, and then the capacity was shifted to crunch. We'll also show the plastic deformation in the steel. To facilitate the visualization, we're going to exclude or make invisible the matrix of the concrete matrix. Now we're going to place the results. Plastic strain. And see what's the result of the cracking steel causing the concrete to take compression. Steel is deformed inelastically in the same area that it was shown in the photograph from the forensic view. At this point, we have completed the presentation of the third part of the three-part series of the building of a 5-story construction, including the design analysis of reinforcement concrete with the bonus of the interaction nonlinear of beam column joints. We'd like to thank you for your attendance. We will remain connected for a few minutes if you have any questions. However, you are welcome to contact us at contact@casolutionscompany.com with any questions or comments, how we could best serve you, and provide us with suggestions what types of webinars you wish to hear, we wish to see us cover. Those participants requiring PDH for Florida, please just request them at contact@casolutionscompany.com, and we'll be glad to provide it electronically in PDF form. Again, thank you for your attendance, and we'll be observing the chat whether you have any questions, and if not, you could always contact us at any time. If you're interested more in the program, let us know, and we can provide you with